Hello, my name is Anestis. I'm a PhD at Robotics and Vision in Medicine Lab at UCL, and this is a short introduction of our ICRA 2018 paper, which is about the requirements-based design and the end-to-end dynamic modeling of a robotic tool for retinal surgery. So as the title indicates, our work is mostly about design, and more specifically, we present a design process which is directed by the dynamics of the robotic manipulator. The new thing that we're adding in the modeling process is the power transmission systems that provide speed and torque conversions in our manipulator, and how they affect its overall dynamics, something that is rarely thoroughly investigated. In particular, we analyze two different types of transmission, namely a warp drive and an anti-backlash lead-through assembly, and we develop equations that describe their dynamic behavior without neglecting the intense friction phenomena that characterize their function. Then we incorporate those equations into existing formulas for robot manipulator dynamics, and we finally obtain generalized equations of motion that describe the dynamics as seen by the actuator side of any robot's link that is moved by any of these particular transmission systems. The purpose now is to use those end-to-end models, and by setting the motion requirements for a particular application, to accurately estimate the power needs and finally to choose the appropriate motorization that will drive the robot that we are designing. Now, the next step of our work includes the application of the presented process for designing a robotic tool for retinal surgery. But before we move to the actual design of the robot, we consider the ergonomical constraints during a surgical procedure by setting the environment for retinal surgery using CAD models that we designed from scratch. Subsequently, we proceed with the design of the robotic manipulator, based on what retinal surgery requires in terms of motion, taking into consideration the spatial conditions that exist into the operation room, and of course by following the presented process to motorize the parts of the system for which we believe that custom solutions might be more appropriate for the needs of this application. The final step includes integration of the designed robotic tool into the surgical environment and testing in order to ensure that the robot's function is within the range of the constraints imposed by the environment itself. To conclude, we believe that the presented dynamics-directed design process will eventually lead to the selection of an optimal robotic solution, as it gives us the chance to choose an appropriate level of customization, keeping the dimensions within the range that would fulfill the requirements of retinal surgery. So that was a brief description of the key ideas that you'll find in our paper. I want to thank you for watching, and I'm looking forward to seeing you in Brisbane.